I go in a slightly different order for Unit 4, so I end up skipping 4.6 and 4.7, and I go directly to 4.8, then 4.9, and then I go backwards. And I have reasons why, so you'll see. Okay, so first we're talking about acids and bases, so you want to make sure that you understand the definitions and stuff. And so for acids and bases, we have a neutralization. So when you add any kind of acid and any kind of base, we neutralize them to make our two different products. And so specifically, you need to know for acid bases the Bronsted-Lowry definitions for these. When we are dealing with Bronsted-Lowry, we're specifically dealing with protons, the H+. As a reminder, if you look at hydrogen, hydrogen has one proton because it's atomic number 1, and if it has no neutrons, then it literally is just one single proton, which is why we usually designate protons as H+. So that is a very common thing to use, so make sure that you know that H+ is a proton. Now, if I'm talking about a Bronsted-Lowry acid, I'm specifically talking about something that donates a proton or something that gives away an H+, however you want to define it. So just make sure you know that. And then for a Bronsted-Lowry base, you want to make sure that you know it's receiving the H+, or it's gaining an H+. That is very, very important. Amphoteric means a substance that can act as an acid or a base. It depends on the situation involved. So one example of this is water. And here is the example right over here. We have two water molecules right here, and so if we assume that this first one corresponds to this one, and this second one corresponds to this one over here, we can look at the hydrogens attached to them to see which one's acting like an acid versus which one is acting like a base. So if I'm looking at this water molecule right here, we can assume this H over here is the same as this H. This H over here has disappeared when it goes from left to right. So that means this H right over here was donated or given away. So since this water molecule right over here donated this H, this water molecule is acting like an acid. Where does it go? This H+ is going directly here. You can see it became 3 over here. And so this H is being received by this water molecule. Because this water molecule is receiving an H, it's acting like a base. And so you can see water can act like an acid or a base depending on the situation. So here's an example of an acid and base reaction. We have to identify the acid and base on both sides of the reaction, actually. When we look at these, we have two sides. We traditionally have the left side being reactant and the right side being product. However, when you have this symbol here in the middle, that is an equilibrium equation. So that means these traditional reactants over here are making these products, but these products are also reacting together to make these reactants. So it's a constant flow. And so since they're constantly going forward and reverse in this reaction, there is no traditional reactant product side. For the purposes of explaining this, we again traditionally do the reactant product thing, but we also use this thing called conjugate, which I'll talk about in a second. So first, we need to identify which ones are the acid and which ones are the base. So let's read this equation like how we normally go from left to right. So if I'm looking here at this left side, I see this HF and water. And so I notice this H over here is being donated to the water. You can see in red the marking over here versus over here. And so since HF gave away that proton, this guy is the acid. Okay. Now, because the water accepted that proton, you can again see that over here, that's going to make this the base. Now, that's for reading this equation from left to right. If I were to go backwards, so I'm seeing this right side and we're making the left side. So you have to focus on what is happening over here to make the things on the left. So H3O, or hydronium, we see this H is going to be donated to that fluoride ion. And so since H is being donated, this is going to be an acid. And since F minus is accepting the electron, that means that's going to be the base. Now, because we have an acid and base on both sides, we need to distinguish which acid and which base are we talking about. So one side of the equation, we're going to label conjugate, and one side we just label as the regular acid and base. Traditionally, the left side is acid base and the right side is conjugate. So on this right side, I'm going to label this as conjugate acid, and then this is going to be the conjugate base. So again, traditionally it's on the right side that we call conjugate, but technically you could say the left side's the conjugates and the right side are just acid base. It really doesn't matter, but you know, College Board prefers tradition, so just go based off tradition. Okay, so we have something called conjugate pairs. And so conjugate pairs are the species where they look the same except they're off by a proton. So if I needed to say the conjugate pairs for this particular reaction, that would correspond to the HF over here and then the F minus. So that would be a conjugate pair, and then the other pair would be these two. So if a problem is asking for the conjugate pair specifically, you want to make sure you write down it's these pairs. So you like list them literally. So another thing that you rarely might see is something called the polyprotic acid. I'm also going to talk about some things that people do that you need to be aware of, but it's technically not how it exists. Okay, so here we have H3PO4. That H is being donated, and then you have your two, conjugate acids and base on the right side. Now, you want to be mindful, because I did not do this on the previous example. This H plus over here is not chilling by itself. In the equation, it looks like that, but that proton needs to be donated to something. So if the only species that's happening in something like this, for example, it can react with water, and so the H plus is actually hanging onto that water to be hydronium. So this is just showing a shorthand of that, but if it's not reacting or like not traditionally reacting and it's just showing the separation, you can't really exist as H plus by itself. So the H plus should really be hydronium, and then on this side you could put plus water. But again, this is just another way of showing stuff like that. So just keep that in mind for any examples you see in the future. Anyway, so H3PO4 has multiple protons that can be donated. That's what a polyprotic acid is. Poly being many, protic meaning proton. And so this is the first step that needs to happen, where one of the H pluses gets donated. And so now we're left with H2PO4. Well, that H2PO4 can then be donating the H plus, and then now you have HPO4. And so then there's still another H that can be donated, so you have that other H being donated, and so now you have all these steps. So the proton that's being donated, they're all different H's, so they're all going to be in different steps. So, like I said, this is a polyprotic acid. Again, rare to see, but I've seen it at least once, so make sure you know that. The shortcut thingy that I was talking about, where this is technically hanging out on water, that's something you should know, though, for sure. Because again, different resources say different things, but H plus cannot exist by itself. Here is a your turn problem. So you want to read the baseline of this question in the first part, and then do each of these subsequent letter parts. For the last one, you just want to explain what's happening using the examples in the equation that you balance. So you want to talk about how do you know that these are acids and bases? How do you know that this is an acid-base reaction? Just literally explain what's happening in the equation and make sure that it is an equilibrium one where you show the double arrows. So go ahead and pause this video and then you'll see your answers in a moment. Ready for the answer? I hope you practiced. Here we go. So you're just writing the reaction as you do. So here it is. Now, I will say you didn't need to know what bisulfate was. That's not one of the ions you actually had to memorize. But for future reference for any STEM class, bi as a prefix usually just means a hydrogen is attached. So if I had sulfate ion, just like straight up sulfate, that would have been SO4 minus 2. But when you have an H attached, well, the H is a proton, so that increases the charge by 1, hence why you see HSO4 minus 1. So the same goes for anything that's a polyatomic, and then you add an H to it. So for example, bicarbonate, that's an ion. You just take the carbonate ion, and then you add a H, and then increase the charge by 1. So that's just an FYI for future you in case you need to memorize that. Cool? Cool. All right. So what are our acids and bases? So here's our acids. So just to make sure you know why, here, this one has to give an H to the water going from left to right when reading this equation. So since it did have one less H, this has to be the acid, again, going from left to right. And so the water is the base because it grabbed that H from the sulfuric acid. Then we have to read this backwards. So if I'm starting on this side and I notice this H3O plus is getting rid of an H and giving it to the HSO4 minus, and so because it's giving away, that has to be the acid. And so all of the stuff that was accepting the proton, those are our bases. So we have the water, and then we have the bisulfate ion. Cool. Then we have the conjugate pairs, so you would need to list them. So one of the conjugate pairs is the sulfuric acid and the bisulfate ion. They're only different because they lost an H between the sulfuric acid and the bisulfate. So that's why they're paired together. And then you have the water and the hydronium. They're different by an additional H to that water, so that's why they are a pair. Now, why is this an acid-base reaction? So essentially, you just need to fully explain it. So here's an example of a way to explain it on an FRQ, for example. So you just need to make sure that you can explain it in a way that's similar to what I have on the screen. It doesn't need to be exactly like this. You just need to explain the process of somebody donating an H+, somebody receiving. And that's it for this, your turn. Here is an example MCQ. So please read this to yourself first and then see if you can figure out the answer. I advise pausing the video real quick and then try it yourself before I talk about it. Okay. I'm going to discuss each option and why the option is correct or incorrect. Okay, so let's start with the first one. So the ammonium acting as a base. So let's look at this equation. We see NH4 here, and then we see that it's donating an H. So it can't be a base. So it can't be A. So automatically can't be A. Now for, let's see, I'm going to skip B and C because those ones are a little harder. Let's go to D. So D, we have ammonium and chloride are a conjugate acid-base pair. Straight up no. So you have the NH4 and the Cl. Well, first of all, there's no Cl mentioned in the reaction. There is a Cl here, which is, just an ion chilling in this reaction, but it's not actually participating in it. Same goes for the Na. So that's why this is just happens to be mentioned. But as a reminder, a conjugate acid-base pair needs to look the same. So can't be that. Okay, so let's talk about B versus C. They're very similar, but how can I know which is which? Well, first of all, we see in this acid-base reaction, this is not equilibrium. If this is a straight arrow going from left to right, that means we assume these two are only making product and these are not making this left side. Now, technically, they could be making a little bit, but not enough. So it's pretty negligible, okay? And so now we have to just look at, well, what does it mean B or C and like that arrow correspond to? Well, reading this problem, I want to emphasize a thing. So it says there is a strong smell of ammonia. So that means we have hella of this. So we are making a ton of that. And we are, again, not making the reverse reaction. Okay? So we need to think about, again, reactions technically being back and forth, even if it's negligible. So who's a stronger guy? Well, NH4 versus water. So if I were to read this backwards, so let's say it is going backwards, this water would donate an H to an NH3. So this would be an acid, this would be the other acid. Those are two acid choices, right? And so because we're making so much ammonia, the NH4 plus has to be the stronger acid because, again, this is not a reversible reaction according to this arrow, and also we just have so much of this. If we didn't have this smell happening, then, that might not be the case. But because we have this strong smell, this NH3 is existing in this reaction a lot in whatever container this is happening in. So that's why that's correct. Okay, now let's look at part C, even though I already talked about part B. So for option C, we have the NH3 is a stronger base compared to OH, right? And so this NH3, again, is accepting, if this was reversed, it's accepting the H from water. This OH is accepting an H from NH4. But again, this is not really acting like a base because we have hella of the NH3 because, again, it is a strong smell. So when you're looking at an MCQ and like looking at the different choices, there are parts of the equation that could have something that you really, really need to know. So again, since we have so much of this because there was a smell to it, this has to exist a lot. And so it's not going to react to form the opposite reaction going from the right side to the left side. Lastly, there's some other acid-base stuff that we don't cover in this class, and you do not need to know for the AP test. I honestly don't know why, because it's not even that big of a deal to know these, but whatever. So, anyway, in your future classes, if you do, have to use acids and bases in some way, there are the other things. So, for example, Lewis acids and bases, you'll learn in OChem. So, right now we're in the Gen Chem of college classes, but we don't really use the Lewis acid base definitions until you're in OChem. Arrhenius is kind of generic. It's not really something to know in terms of definition, but you can look it up if you prefer to know for any, again, future course you may take. So, overall, you need to identify acid bases. You need to be able to see a reaction and know for sure it's an acid base. You need to know conjugate pairs. You need to know the reversibility of reactions or the lack of reversibility, like the MCQ. So that's it. All right. I hope you have a good rest of your day. Bye.